Zeyi graduated from biostats at Hopkins last year. No, 2 years ago. I've lost track of time.
Last year.
Wait,
last year.
You just graduated?
No. I mean,
what? You
it
graduated?
has been a year since I graduated. It's been a year and a half.
Yeah. Okay. And at Hopkins, he worked with Brian Caffo and others, and then has pivoted and is now a postdoc at Berkeley with Mark Vanderlaan, where he's working on the most amazing semi-parametric theory, higher order influence functions. And I'm really excited to hear about this work today. So thank you very much for visiting, Zeyi.
Yeah, I appreciate a lot for this opportunity to contribute to this series. So it's really nice to see you guys. The topic today I prepared is the computerized higher order efficient estimation. So this is a extension work on the previous higher order TME paper. So some of the idea has been discussed in that tech report. So I also put a link here. But to get to this project, so I will start maybe by introducing some of the background. I'm sure many of you are very familiar with it. So basically our problem setting is always about estimating a finite dimensional parameter. So some psi of p, where the p can be some data distribution that can be fitted with different machine learning techniques. For that seemingly simple question, and direct option would be just to do a plugin of the machine learning fitting. So that idea turns out to be not that ideal for various different reasons. Sometimes the estimation model can be in ultra high dimensions and also involving different variable selections, which can all impact our asymptotic behavior of the plugin estimation. And then sometimes if people really want to respect the true data knowledge, they will find out they have to put some weird model restrictions, which just can put some extra difficulties when they try to analyze the data, analyze the behavior of the estimator. So just in general, that the direct plugging of those machine learning techniques, those seem very promising, but usually fails to provide reliable results. So here is at least one example that I like the most, the simple and direct, that we think about just the simplest treatment-specific mean example. So we have baseline covariate as W, treatment node as A, outcome as Y. Both A and Y are binary. And we just assume all the regular identification assumptions, such as the counterfactuals are, we observe those values in real data with consistency, and we observe the propensity score with positivity. And also we assume the conditional equilibrium just usual identification assumptions. And that we consider the psi of p here being the treatment of the mean. So there's nothing special about that. So now if we say how about we do a linear regression of the Y on A and W, but we do a pre-screening of the variables on W using a Lasso selection procedure. So just a regular linear regression with some variable selection, one might think that would just give us because it's simple, that might be reliable, right? But turns out that can also be problematic. Like if we say that if there exists a meaningful confounder X in that the baseline covariate vector W, and if we just assume the true relation is thus such that the coefficient beta 1 is decreasing in the order of square root log n divided by square root n. If that's the case, then the lasso will have a probability going to 1 to drop this variable, and that in turn will give us an asymptotic bias going to infinity. So that's one simple example to show the problem of that. So of course, this is a long-known question. So one of the solution is the framework of targeted maximum likelihood estimation. So since the direct plugin would not be a good idea, so we might think about how about we plug in something a little bit better than the initial fitting. And to achieve that, we just do some minimal extra data fitting. Essentially, we'll look at, so to understand this procedure, I'm sure many of you are already very familiar about it, is that for the TME update, some Pn star of the initial distribution estimator, we can look at this exact expansion. So there is no derivation here. It's just the expansion as it is, and we can look at this leading term here. If we really want this one to be the leading term, so that our estimator behaves as a asymptotic linear estimator with an influence function d of b, then we must have the three terms, so the three remaining terms, they have to go into zero in the second order as a second order term. So for that, we can look at them one by one. So the first one is essentially comes down to how fast our distribution estimator can converge, and also we cannot have a too crazy complex efficient influence function estimation. But in fact, that assumption, a part of it can be relaxed by, say, data splitting. So we won't have too many details for this part, but we just say that this assumption is one of the ones that is weaker assumptions here. And the second one, we look at the term and we realize that this requires to solve an estimating equation consisting of that influence function we had in mind. And to solve that, this is where the so-called targeting steps comes into enhance. So we use the targeting steps to make sure that our TME update will solve these estimating equations, where our initial estimations, the direct machine learning estimation plugin might not have this property. So this can be either solved to be exactly zero or to be solved to some converging term. But the general idea is that this is a part that can be handled by this regular TMLE machinery. So the last is the third part, called the exact remainder. Removing the other easier terms. So for this one, we wanted to also to be a second order term. And what we usually have in practice, for example, in many data coarsening at random problems, is that it involves cross products of the different likelihood factors. So we have more than one chance to have a consistent estimation. For example, in the previous example, if we do the target maximum likelihood, we will have a extra chance if our propensity score model is correct, even if our lasso screening estimator might be wrong. So in that sense, what our previous work with higher order TMLE does is that it further relaxes our assumption on this remainder, the last remainder term, to not, it doesn't have to be the second order term anymore, but can be converging to zero at a lower speed.
Sorry, Zeyi, can we pause for a second? So is the idea, I'm confused a little bit about how this relates to the lasso example that you gave. It seems like that, how does this address, I guess I see how a double robustness property addresses the problem with the lasso screening failing to pick up an important confounder. But if you're still using lasso for the outcome regression component, it still would have that problem, right?
I think that's a legitimate question. Like if the both models are wrong, there's still some issue. But the idea, at least we have at least first we had one extra chance. That's first.
With the propensity
one extra chance. if the parameter is correct. And then second, if we use the higher order TMLE here, we'll immediately realize that we no longer require the remainder term to be second order. It can be, if we can directly have this one.
Okay, so in that case, you would just relax the lasso structure to a model that converges slower. Is that the idea?
Yes.
Like,
yes.
okay, so
and,
you would have a lower penalty.
Yeah.
Okay.
Yeah. So illustration example, but it just come in handy here if we check the order of convergence, it will be covered by the.
Yeah, that I get. So the idea, correct me if I'm wrong, this is my understanding of higher order influence functions. Normally, to figure out the asymptotic distribution of an estimator, we do the Taylor series expansion, we look at the first order term, and we make enough assumptions so that all of the lower order terms go to zero quickly. Higher order influence functions allow you to let the higher order terms go to zero more slowly, but you're going to show us a trick that essentially removes the bias due to those higher order terms. Is that correct?
I'll do a little bit different trick to avoid the higher order gradient calculations, but I will utilize the existing machinery like how to debiasing with the lower convergence speed. I will just use those existing results for that part. But the general idea, yes, for the initial estimator converging in slower speed, we can now have better reliability of our estimation and inference. And for the distribution estimator converging at the same speed, we can have a better debiasing result.
Okay, thank you.
Please stop me. And I'm just really excited about this part. So any questions will be really helpful. From the discussion so far, we can see at the core of this problem, we also need some knowledge about the canonical gradient or efficient influence function, to say the least. So we know that the regular asymptotic linear estimators will have an influence function that is also a gradient. That just means that for a class of submodels, we always have the directional derivative to be represented as a inner product between this gradient and the corresponding score of that submodel. And our tangent space is just defined as a linear span of all the corresponding scores of our interest. So among all these regular asymptotic linear estimators, it's a known result that the smallest asymptotic variance or covariance is achieved at the efficient influence function, which uniquely exists in the tangent space. And if the tangent space span the whole space of mean zero finite variance function, we have only one gradient, and the gradient is the canonical gradient. And that's some general idea. So there are a number of different techniques, the Causal derivatives, functional delta methods, and also some projection ideas. If you really like the yes, that's a nice typo. Thank you. For the if you are familiar with the Seattle's idea, so there are some examples here for the simple psi-p being the probability of univariate O greater than 5. We have the simple efficient influence function just as indicator minus target parameter. For treatment specific mean, we have a very famous representation of this influence function. It can be derived in different ways listed above, but we can also realize for the non-parametric models, this will be also the canonical gradient. However, the challenge we want to tackle with this project is that in practice, not always this efficient influence function can be easily derived. And in many scenarios, even if we have the closed form expression for it, it can still be computationally too expensive. And also with the context of higher order TMLE, the higher order canonical gradient can also be something that just make people really fear about it and not really derive it. So that can be an issue that we want to solve with this project. So here is our general problem setting for this project. So imagine we have still an ID data, and then we just care about like one intervention of interest on the data distribution. Taking the treatment specimen as an example, our intervened conditional distribution of y is just a regular distribution of y plugging in the treatment node being 1. And also, we don't have to always consider the deterministic intervention like this. We can also adopt a random interventions. So if our data is a multiple node from y1 to y tau, and we have a decomposition of our joint likelihood as such, is a flexible one. There's no special requirement. We can define our intervention of interest by just replacing some of these likelihood factors with known or factors that can be fitted from the observed data. So these can cover a number of different target parameters. For example, if the underlying data is some network data or imaging data, where we have extra model assumptions, sometimes can puzzle people about how to derive the efficiency function for regular TME and higher order TME, but at least the intervention can be fully understood. And that's what basically all we need here. So for that intervention distribution, our target parameter is just a mean level under that intervention distribution. So the idea of computerized higher order TME you want to do with this project is to say, so just leave the, so just let the data scientists do their work for the all the part above, so they can really be relaxed, so they can utilize any knowledge they know from the data without being in fear of not knowing how to conduct the late follow-up efficiency estimation. But then we let the computer just to decide what the canonical gradient should be and what the efficient estimate should be. So that's the idea. Of course, that's a very ambitious goal. So for this as a starter, I hope to do a proof of concept to say with simple examples or realistic like mediation problems or treatment specific mean problems, we can at least see that the numerical gradient will give comparable result with the analytical one. For our method, so the idea starts with some basis representation of the tangent space. So starting from the simplest scenario, conditioning a conditional density of y given x, if you consider the tangent space just being all the mean zero function conditional x of y and x. If we want to, if we like to assume a basis representation of that space, we can think of a collection of basis functions that can span first all the functions of x and y in this format. So those are the type of basis functions usually used by the highly adaptive Lasso algorithm. And then we can center those bases to represent this tangent space. So for now, we can, as a starter, we can assume that is an exact representation of the tangent space. And if we have longitudinal data with the specific time ordering, we have the decomposition, also the decomposition of the tangent space for each of the conditional likelihood factors. So now
Sorry, I just want to make sure I'm following. I think I got that, but when you center the basis functions, you're just ensuring that the conditional expectation given x is 0?
Yeah, it does just that.
Okay, so, okay, got it. Thank you.
Yeah. So I just start from an initial set of basis function, and the centering does nothing but just to approximate this tangent space.
That's
here.
Cool. I hadn't seen that before.
Thanks. And then recall our target parameter is just the mean of our outcome node under the intervention distribution, and we intervene some of the variables So we replace some of the likelihood with P star, but some others remain the same. And then for our pathwise derivative analysis, we now need to think about what are the score functions that we care about. So then it immediately comes to my mind that we probably need to cover all the centered basis function we just discussed above, because our assumption was that those centered basis function will span our tangent space, and then our canonical gradient will sit in our tangent space. So they will also be represented by those scores. So it will be the direct thought to link the canonical gradient and to evaluate those pathwise derivatives along those specific path with those centered basis as the score function. So we can, for the kth conditional mean of interest, we can define this submodel by, say, we only fluctuate one of the node, that is the node of interest, and then we fluctuate with the model so that the score will be exactly equal to the centered basis. And then we can think of it in two ways. First, as the pathwise derivative, we can evaluate these the target parameter values at these two distributions. And then we can realize that the only difference of the P at this fluctuated P and this original P is that there is some 1 plus delta term here. And if you take derivative according to delta, we'll end up with a expectation of outcome node times that centered basis under the interval distribution P star. So we have in hand what the directional derivative value should be. And then on the other hand, because those are the paths of interest, we know the canonical gradient should represent those pathwise derivative as an inner product of the canonical gradient and the corresponding score. So we'll know that the other expression of it is the expectation under P, not P star, the P of this canonical gradient and the corresponding centered basis. And then if we plug in our linear combination representation of the canonical gradient, after some derivation, we'll immediately see that with the known vector of directional derivative and then a covariance matrix of the centered basis, we can essentially solve a equation system to get the coefficient for canonical gradient. And that can be done by a classical decomposition of our covariance matrix of the centered basis. So that's the first representation here. So if we assume that our tangent space is exactly represented by those bases. So then we can move us a little bit one step further, that all these basis representations, they are nothing special. So we can use a different set of bases. We can do a little more orthonormalization of those bases. So we can, for example, use the Gram-Smith process. So we can get a transformed set of bases where the first k new basis will only utilize the first k original basis. In that way, because they're orthonormalized, the inverse of the covariance matrix will just be the identity matrix. In that way, we can get the coefficient for the new set of bases directly through that expectation under P star. And also because it's a also normalized set of bases, if it is represented by a infinitely many of Gram-Smith spaces transformed from the whole basis, highly adaptive Lasso basis, we know immediately from the basis inequality that the coefficient will converge to 0 because of if our canonical gradient is something with finite variance. So that will give us.
Sorry, I'll let you finish the sentence.
Yeah, finished.
Can you explain why you're transforming to in like a high level picture for why you're transforming to an orthonormalized basis? Maybe
just to find.
Yeah, sorry.
Oh, the first just for fun, and then second is just to find a instruction on how to decide the number of bases we will need. So because here we know the coefficient will converge to 0, so we know that even if the canonical gradient is represented by infinitely many of basis functions, in practice, for numerical calculation purpose, we won't need them all because it's a converging sequence.
Huh. Okay. So
And
it gives you a way to regularize the number of basis functions in finite samples. Is that
that's
right interpretation?
Yes. So just do so. Otherwise, like we can look at this expression, and we immediately realize that we have infinitely many basis functions to choose from, and how to decide which to include. We know that the matrix inverse can be unstable with tens of thousands of dimensions. We don't want to include all of them. So there is I try to find some guidance on how to find it sequentially and also in a scalable way. Okay. So this is one of the guidance we can have. We can have some simulation result.
Thank you.
Can I also ask a question related to that? So this seems like a brilliant idea to orthonormalize the basis so that you can justify, you only need to choose finitely many of these basis functions for the approximation. Do you know if this idea is used in other areas in statistics where basis functions are used, like functional analysis or other areas? I'm just curious.
Yeah. So Tianchen, you must know better about the functional analysis than me. So
not really.
but for this one, I haven't seen an immediate example of using this because it's due to a special relation in terms of the pathwise derivative. So I found this kind of interesting at first as well.
Thank you.
Yeah. So
wait, I can't follow that. Which part of what you said is specific to the pathwise derivative?
Yeah.
Sorry.
So we calculate. So for this part, we calculate the pathwise derivative for all the bases, for all the centered bases we discussed about. So for all these basis functions, this pathwise derivative has a closed form as this, and so we can link this vector of pathwise derivative values with the canonical gradient representation of the pathwise derivative. So after we link these two, that's where we can get this exact relation of these two. So for the scenario where the tangent space is exactly represented by those spaces, this will be an exact relation. So there's no approximation going on if that's the case.
And you need that to be the case in order for orthogonalizing to work the way you want it to? Is that that's the step I'm missing?
Oh, if we skip the orthonormalizing steps, I have just found it difficult to find a reliable guidance of when to stop including more of the bases.
Yeah, no, I'm wondering about Tianchen's question. Why don't people orthogonalize basis functions every time they use them?
Yeah, in other words, what's so special with your particular TMLE problem that enables you to justify the use of these orthonormalized bases?
I have an answer, but maybe it's a little bit trivial coming back to the question is that I then show that it's just the same representation as the previous Klasky decomposition, but just do it sequentially. So
and that wouldn't always be the case. Okay.
So that will, yeah, so this representation will not give too much more information compared to just the original representation, but we just get one more guidance on the convergence rule. So
I'll take your word for it. Maybe Tianchen can understand it and explain it.
Not yet, but I think I need to read the paper to think more about it. Yeah, thank you.
So yeah, so if we just take the first few bases, either the centered one or the transformed one, And if we project a canonical gradient onto the space spanned by those first few bases, we can immediately see this relation so that we can know that the transition matrix to get the orthonormalization is just the classical decomposition matrix and taking an inverse. So there's no extra calculation needed to achieve this convergence rule, but just nice to have the representation here. So maybe I can just show one example here. So for to demonstrate how in real data it looks like. So for all these plots, we include more and more bases in the data set of sample size 200, and we have 8 continuous variable W and the binary A and binary Y. So for the first plot, we can see when we include more and more bases, we can see increased correlation between estimated efficient function and the exact efficient impedance function, and also the decreased mean square error of estimating that. In the third plot, we see the L2 norm of the Gram-Smith coefficient dropping to a level below 1%. So that's the increment of the new basis provided to the L2 norm. So we can see that how these guidance can help us in deciding the when to stop. But of course, we can look at the empirical mean of our numerical efficient directly. We can see the increment after including more and more bases. Those increments go into 0, and we can see the empirical mean of the numerical gradient is somewhat plateaued when we include more bases. So we can, for each of these dots, we can stop there and conduct this TMI estimation. So in the last plot, we just do that. For those, all these red dots are the TMI estimations. If we just stop there using those bases and just do TMI, and we can see if we follow the guidance from the L2 norm, they will give us a estimation at the dotted red line that is quite close to the solid line from the exact TMI estimation. That's the so I think the Gram-Smith representation just gives us one more very handy guidance on the upper right here. Like we can look at keep track of the L2 norm of the coefficients, and that's where it becomes handy. Yeah, so that's the first type of representation. And then we don't have to implement that if we have some other alternative options, like if we have an initial gradient following the relation that once we project it onto the tangent space, we get the canonical gradient. If that's the case, and that is quite common in coordinate random problems, then we can select those spaces and estimate those coefficients directly from this projection expression. So that can be, it doesn't have to go through the sequential classical update steps we discussed above, but we can achieve this by just one highly adaptive lasso fitting. So we basically have two ways in hand. So the first simulation is just that if we, again, coming back to the idea, if everything is discrete, we have exact representation. So there's really no data to show that. It's just the canonical gradient is being exactly the same as the exact one. And then for the continuous data, we discussed a one run. But if we repeatedly sample the data and look at the performance, we can see that the GRM estimation and the TMI estimate using exact inference function and TMI using numerical inference function. So those two TMI estimates will perform quite comparable with either correct models or under rare events or under model misspecification, or sometimes even slightly better in the bias reduction. So that's the first type of efficient inference representation using the sequential classical updates. And then for the second option, we use the initial mapping, So this is an example with the longitudinal mediation problem. So following our previous discussion, our intervention of interest is just say we treat every node except for the mediator node as if they are treated, and then we treat the mediator as if they are in the control. So the mean level under that intervention is of interest to differentiate the effect directly from the treatment versus the effect coming through the mediator. So for that target parameter, we know the G computation formula. That's the expectation under the intervening distribution. So that's all we need to know. So starting from there, we have the initial mapping to get to the efficient inference function as such. And with that projection, we can decide the basis and the coefficient directly. So this is the simulation with the correct model or misspecified outcome model. We can again see that using the projected influence function and the exact influence function, resulting in quite comparable performance of the TMLE estimation. So far is about the first order TMLE, and if we are concerned about the higher order TMLE, we can skip some of the details here, but the general idea here is that we will need to solve more score functions, and those score functions are the higher order canonical gradient. And because we have that basis function, and we can keep using that basis representation. So say if we keep the same set of bases and try to represent the higher order canonical gradient, we will actually get a quite similar representation with the same matrix inverse of the covariance matrix, and only a different vector of pacified derivative values. So the only difference is that now the pacified derivative will be calculated for the higher order data adaptive target parameter, not the original target parameter. That's the only difference. So we can even keep the sigma matrix the same. So to get that vector, we can do some calculation here. So after just a few steps, we can get something that that can be tracked from our previous updates. So if we want to calculate the second order TMLE, as long as we can keep track with the first order TMLE updates at the initial P and also the slightly fluctuated P, we don't need anything else to get this pacified derivative. So that means this procedure can be directly followed after the first order TMLE. And second, we can even approach to higher order TMLE without any further calculation, and to repeat this step and keep tracking the lower order updates. But for this part, it's still under active development. So this is it's a simple simulation, still proof of concept with fewer variables and fewer sample size. But we can already see that compared to the first order TMLE using numerical representation, the second order always improve the debiasing result. So for those simulation results, it will come as our purpose of this first project is that we want to show they are comparable in the sense that, so this is, for this simulation, this is the scenario we know exactly what the canonical gradient is, and it has a very simple format. But for the scenario where the canonical gradient is not that accessible and or computationally too expensive, we can still easily, with the same procedure, to calculate the numerical version and follow up higher order TMLE even, just by knowing the intervention distribution. So I think that's the should be the summary for the talk. So first we have a new representation. So one by the sequential classical updates of the Gram-Smith basis, and the second is the projection of the initial gradient onto the tangent spaces. Both can result in a initial set of bases, and using those bases, we can get the higher order TMAE estimations quite easily. And then from our so the idea of computerized estimation is that we can let the computer decide what the numerical clinical gradient should be, and what the estimation should be following the same procedure. So without knowing extra algebra knowledge on our parameter and our influence function. And from our simulation results so far, we can see comparable results for analytic and numerical versions influence functions using TMAE estimation. And with that in hand, we know that the numerical version will be easily extended for higher order TMAE without too much calculation, like we have the exact version. So we need a closed form higher order gradients. Sometimes can be difficult to calculate. Okay, so that's some references.
Very cool. Thank you, Zeyi.
Thank you for the questions.
I have so many questions, but I'll see if anybody else wants to jump in first. Okay, my questions are really going to betray my ignorance here. My goal would be to understand all of this at a high level so that maybe someday I can sit down with the paper and really understand the details, but I'm still not confident that I understand it at a high level. At what stage are you building in semi-parametric or parametric assumptions? Or you're not, this is not only for the non-parametric influence function, right? It can be for.
Yeah, that's a fair question. Like for the semi-parametric models, we need to approximate that tangent space differently as well, but that can be just by putting restrictions on those basis functions. That's one of the things we.
Oh,
yeah,
sorry.
I like to.
That's future work. Is that what you were going to say?
Yeah, that's one of the things we haven't implemented yet.
Okay.
But we can imagine that for some of the difficult projections involved with the semi-parametric assumptions, so to get those projections with the basis functions can sometimes be easier. But that's the instincts we have now, but we haven't implemented that. But that's an immediate next step.
So is it fair to say that you have to trade off which is easier, deriving basis functions for a semi-parametric model or deriving the gradients algebraic directly? And maybe, yeah, if your model is very simple, it might be easier to just go for or if you already know the gradient, the canonical gradient, you'd go for that. But if it's I guess I'll wait for your future work to see when one would be easier than the other.
Like for taking the longitudinal mediation example, the canonical gradient is known, but involves repeated integrals. So make it really difficult to use because it takes a longer computational time. So for this simulation, although we compared the exact influence function and the projected one, the running time is really like 10 times slower. So to get the same result, and even when we have more time points, the exact version will just fail to run. So that's one benefit to have this.
Okay. I said I have so many questions, but I don't, my other questions would be like, can you give the talk again so I can try to absorb it again? I don't.
Yes. Yeah, but I think it will be a good next step to show an example where the sample model can be approximated easily with those basis representations, whereas the regular projection can be difficult to derive. That would be the next step here. I can think of some simple scenarios if we just put like if we just restrict the range of values for each variables, then just adding some additional indicators to this. That would be very simple to derive. But for, yeah, it will be, I will need to think about more like a general way to express those projections clearly. But I think that's an interesting direction.
And then so would this, your basis function, in what you've presented today, the basis functions are for an entirely non-parametric model. Is that correct? And so,
yes,
so the comparison would be not to something like Lasso. It would, the comparison would be to an like standard TMLE that had a fully non-parametric outcome regression, right? And that, or I guess I'm confused about the rates of convergence here. Like if you need quarter root convergence rates on the propensity score model and the outcome model, oh, I guess that just constrains, that's a constraint on the complexity of the true DGP, not on the methods you use to estimate. Is that correct?
I'm trying to understand the convergence speed. Part of the convergence can be controlled. So for this basis representation part, it can be controlled. Like for those, where is it? So for the representation, we'll always need to pre-select some set of bases, and we need to order them in advance. And if we choose those bases from the observed data, we will essentially get a numerical approximation converging to a highly adaptive lasso fit with this sample size of n. So that is already enough to maintain asymptotic behavior, but we don't have to do that. We can generate the data at P and get more bases, and essentially we can as many bases as we want. So this part of the approximation, so the approximation error for the numerical inference function is something that can be controlled. So we have a controlled precision for this part. So this is independent from the other requirement on the convergence speed of the other part of the distribution estimation. For example, in our simulation, we have the true model being just logistic, but our model assumption is fully non-parametric. So that's the case here. So when we use logistic, we have a guaranteed fast convergence. And yeah, we can actually see some little bit increase in bias and standard deviation due to the use of approximated canonical gradient, but we don't see like a trend that really comparable in the performance. Like we still maintain the essentially the asymptotic behavior of the estimator. So that can also be like a verification here. So it's two separate. So the precision of the basis representation can be controlled. And the other thing is the regular requirement on the distribution convergence. That part is not impacted by this.
Right. The distributions still have to be of low enough complexity.
Yeah. That will just follow the regular TMLE and high order TMLE requirement. Like we have second order or lower convergence rate, depending on the order of TMLE you want to do.
Yes, okay. This is a bit of a divergence, but can you explain what highly adaptive lasso is in a few sentences?
Yeah, like that's something I found really amazing and puzzling at first. Like if we just consider all these type of basis functions and say, what are the type of functions we can generate from all these type of bases? And that can cover actually all the functions with finite total variation norm.
Mm-hmm.
Of course, with the higher dimension vector of x, we go through a special integral step by step for each subvector of x. But the idea is still we want to achieve at a linear combination of these type of basis functions. And to achieve that, we know that the only requirement, the only restriction is in that the total variation norm is bounded.
Okay.
And the only hyperparameter we need to choose is that bound on the total variation norm. And that just becomes the Lasso problem. So we need to, and they're actually fitted with the same hyperparameter on that total variation norm. And so we can just put in those bases into a lasso fitting.
So it's a lasso where the covariates are the basis functions and the lasso tuning parameter corresponds to the bound on the total variation norm.
Yeah, that's my simple understanding on this.
Whoa.
So that's also the reason why we have this simulation with, for the simpler simulation, we just use the observed data to generate the basis functions, because we know that when we include all of them, it will just converge to the highly adaptive Lasso fitting, which will already have a good convergence rate.
And does it work well in practice? How does the performance of highly adaptive Lasso compare to other non-parametric model estimating procedures?
For me, it can take longer to run with larger sample sizes, that I have to admit, but I find it really useful when I have something that I want to really like guarantee the convergence, like for this longitudinal mediation analysis, when I want to make the projection to be something convert with a guaranteed converting rate. So where is it? So I did that projection using the highly adaptive Lasso to guarantee that. And in our project, I can make the dimension reduction in a special way, so I can maintain most of the information from the previous data. So in fact, I always only need to feed a relatively fewer dimension highly adaptive Lasso, which I found is very useful. But for more complex scenarios, I don't think it's not scalable. I think it is like from our, and also from our simulation here, for sample size 100, we don't need to include all the basis functions. Actually, from our simulation, we already see that only a very few basis functions can give us a very good approximation here. So I think there are rooms for the implementation of highly adaptive Lasso. So we can imagine if we include all the observed bases for all the directions that will, and for more variables like more than 100 variables, that can be a huge number of basis functions that cannot be handled by the regular computer. But in reality, is that we only need very few of them. So I think that's another room of improvement.
Yeah, I guess I'm curious to know if that, and I don't know how you would know when you don't know the truth, but I'm curious to know if that holds in real data where the data generating process could be quite complicated and you just want a good low to medium dimensional approximation. I don't, yeah.
As long as it's reasonable to assume on the total variation norm bound. And
yeah.
Also there's some result on the rate of number of bases needed. So that's not increasing too crazy. So we just need to smartly choose them. So for this project it's quite interesting that we can directly evaluate how well we are doing with the existing bases. So on one hand, we know we don't need too many, and secondly, we can do it sequentially, so it's a scalable process. But in the real data, I think it's still room for improvement, like how to smartly choose those bases.
I see that we're up against 1:30. Thank you so much, Zeyi. We might
thank you.
Keep us posted as you produce more research along these lines. I would love for you to keep coming back and keep us posted about your work.
Thank you so much for all the questions are really helpful for me to move forward with this project, and appreciate this opportunity to come back. Really always enjoy coming back.
It's really nice.
Thank you so much.
Thanks so much, Zeyi. We appreciate it.
Thank you, Brian.